Hey, I'm Salwa Mostafa. I'm postdoctoral researcher at the University of Oulu, Finland. I will be talking about our work for the EU project 6G Intense, RAG-enabled intent reasoning for application network interaction. First, I will give a brief introduction about intent-based networking, talking about the state of the art, state the problem under consideration in this work, and introduce our proposed framework as a solution, showing some of the experimental results, and concluding the main finding for this work. 5G and beyond networks are expecting to support different applications and services like augmented virtual reality, cloud gaming, smart industry, and each of these applications have their own requirement and needs to be satisfied uh, from the network. So, because of the large number of applications expected to be supported, relying on traditional manual configuration becomes unreliable now and more complex for network operators to manage. So, most network service providers are moving toward automating network operation and management. So, intent-based networking has been introduced as a simplified and efficient way to automate the network operation and management, where we need to understand what the network users or applications want and what the network operators can offer and try to optimize between both of them. Intent, what we mean by intent, it has been defined as a high-level description of what we expect the network users expect from the network as an outcome or a service, without specifying how the detailed implementation for this service or application should be implemented by the network. This gives the network operators a great freedom in expressing, in implementing the service and optimize their network resources. So the intent is a very high level description for what the network users expect from the network without specifying how it should be implemented. And it takes uh, a complete life cycle, which takes place over 5 main steps. It starts with intent profiling, where the network users express their needs or expectation from the network in a very high level. Then we have the intent translators, which as act as to translate or convert this high level abstract service into network policies, configuration, machine readable devices that the network can later on uh, use to activate the network functions and devices. We have also intent resolution, which help to resolve the conflict between independently submitted intents. And we have the intent activation, which activate the corresponding policies and configuration in lower devices and functions in the network. And we have the intent assurance, which monitor the performance of the intent or the life cycle of the intent to ensure that the successful deployment during the life cycle of the intent until the expected service has been delivered to the network user. Um, we will only focus on the first two parts of the intent-based life cycle, which is uh, uh, intent profiling and the translation. So in the state of the art, we will cover the first two main components of the intent life cycle and talk about our proposed framework for this part. Um, Over the years, there have been several user input methods proposed for the network users to express their intent to the network. One of them is to rely on API, where the users use command line interfaces API JSON files to communicate with the network. Uh, of course, it's a very simple way, and it clearly express the intent, which reduce the complexity of intent translation, but it requires the network users to be expert or having some background about the technical details of the network, which sometimes is not possible for normal users. Then we have also a template or geographical user interface, like the one shown here, where the users have a drop-down menu. They can choose the quality of service level, the security level, the start and ending time of the service required from the network. It's very easy and simple to use this method, but it has on the other hand, it has limited options where the user cannot express their intent outside the scope of the predefined list for them. Later on, natural language has been introduced, where it has a free way for the network users to express their needs to the network in a human language. The advantage of that is the users can express what they expect from network as a service in very in a free way, but on the other hand, it also complicated the translation the translation part, because we have diverse number of users with different background, like some are expert and have some knowledge about the network operation technical details. Some users are not, and we have different users from application developers, network operators, and end users. So the translation process becomes more complicated to be managed. The existing methods for translation rely on using machine learning to classify the intent or abstract some keywords from the expressed intent to identify what the network needs to do, or carry on the implementation of the intent. And these methods rely on extracting some keywords and later on mapping it to network policy. And this requires a large labeled data set, so that you are able to map the extracted keywords to network policies. And it's until now we have a lack in providing accurate data set for that. And it's also over the year have been NLP were good for simple intent, but when the intent is very vague or complex, it has difficulty in translating it. So in this work, we discuss or investigate the problem of interaction between different user application and network service providers, where in IPAN we aim to provide human tailored network interaction, where the IPAN speaks the language of the network users instead of asking the network users to learn the language of the network. So we want to take the high level expressed intent from different user applications and try to translate it to network language that um, the network can be later on used for implementing the required network functions and configuration. So we have different user applications, like users using VR, V2X. All of these users aim to connect with the network and express what they expect uh, as a service from the network for these applications in their own language, like the human language, and it's from different background or it's specific to different applications within the domain of each application. What we mean by domain language is that uh, the users express their expectation from the network in a very high level and related to the application, in a very abstract and high level related to the application itself. For example, if we say that a user is using a VR application and the user wants to express, I want like VR without motion sickness, it's a very high level description, and somehow the network needs to figure out what is the quality of service required so that the user have the expected service. So for each application, they have different domain language and expectation how the application should be supported from the user, from the end user perspective. So creating a semantic language or ontology-based language associating with each application was quite unscalable and lacks technical expertise to do that. So recently, large language models has shown a great capability in reasoning and understanding the human language and do some interpretation based on this. So we propose a context-aware AI framework which utilize machine learning, retrieval augmented generation, and generative AI techniques to interpret the intent from different applications and construct a network intent that can be processed by the network uh, um later on to do the implementation for the required functions and services. Our framework mainly consists of three main components. Knowledge base, where we chunk the technical documents, embed them, store them in a vector database. We have intent refinement, where we receive the high level description from different network user domain, do some interpretation and convert it into a well-defined intent that can be used to search the network database. But what we mean by well-defined intent is that it has the main keywords, that technical keywords that can be used to search the network database about the right network policy or configuration. Then we have the structured intent creator, where it is extracted the relevant information to the submitted intent from the network database to implement, to later on generate the required network intent that can be deployed by the network or understood by the network later on. We will talk briefly about how we do the detailed implementation for each of these three blocks. So we start with the knowledge database, where we have the technical documents. It has different modalities, table, text, image. We pre-process these documents using unstructured tool, where we extract each model and use the synthesis splitter with certain chunk size and overlap. It all of this is detailed implementation depends on the documents itself, and its parameters are chosen based on experimental trial. And for each of these models, we create a summarization pipeline where we we get out a summarization for each of these models and store the model with its summarization by embedding it using one OpenAI embedding model and store it in a Chroma database. To do that, we used a summarization LLM model already trained to do summarization, and we write a specific prompt to do for each model. We do the implementation and then store it in a vector database. In the second block, we do intent refinement, where the user submits their intent, and we have a domain guidance which related to what the domain where we receive the intent. We expect that we know what kind of intent should be received or expected to be received from which domain. For example, it's from end users or applications, so it's more general intent, or it's coming from the network operation, so we know it's a technical, and what is the scope of this intent. It's coming to, for example, RAN, core transport network, so we expect in which domain this intent is submitted. So we have some domain guidance telling us what, based on what the scope of this intent, we query the network database to get some information that helps the LLM interpret the intent that has been submitted. So in the intent refinement, we give a very the specific use case we use in this work is that we have a service provider for different services and traffic scenarios, and for each of these traffic scenarios, we need to interpret which service or traffic scenario the user is requesting from the network. So the domain guidance in this case is is asking like a query engine to the network database to list all the service or traffic scenarios that provided to the customers, and based on this list we try to guide the LLM to map the general user intent to one of these services or traffic scenario. So we have the query engine that receives the domain guidance, and the output of this query engine is passed to a prompt. This prompt receives the user general intent, the guidance instructions from the network, and it has some few short examples to improve the reasoning capability of the LLM. So it gives some example how it should interpret. For example, if the intent submitted, say I want internet access with fast browsing services in an aeroplane, then the LLM can interpret that the service required is aeroplane connectivity, and the network has the configuration for this specific network service or traffic. And then we submit the problem to one of the LLM models that already have a reasoning capability. And then we take this well-defined intent later on to the next block, which is structured intent creator that receives this well-defined intent, embed it and send it to a network retriever to retrieve some specific information or configuration about this service. And based on this retrieved information, we do re-ranking and list the top 3 out of this retrieved content and pass it to the prompt to create the intent based on the network knowledge. And the prompt also is provided by some simple examples, the few-shot learning, to improve its performance and accuracy when it creates the structured network intent. And we also use an LLM model that has trained on doing some structure in a specific format. In our experimental results, as I said, we use specific documents related to service and traffic scenarios provided from a network service provider to users. And we use also one of the baselines, vanilla rag, which is does not do all the optimization we done at each of the blocks in the framework. At each of these blocks, we try to optimize the performance of this block by choosing which models to use and how to do the process inside each block. For vanilla rag, we just use the native rag, which retrieves the knowledge directly from the network database and retrieves the top related context and put them without any re-ranking. And we use the same prompt in both of them for fair comparison. So based on this result, we have done the evaluation, human evaluation, by comparing the output for different scenario between vanilla rag, our proposed intent rag, and using large language models directly without doing any rag. And we have the ground truth, which extracted from the document itself. As we can see, we find that intent reg gives more accurate output compared to the ground truth than vanilla reg, and for LLM it hallucinates a lot and gives more large context because it accesses a wide database. When we use reg, we just stick with the network documents, so we reduce the hallucination from the LLM. We also use the RAGAS evaluator to evaluate the retrieval part and the generative part in the RAG. And for the retrieval part, as we can see, that the intent RAG has better context precision, context recall, and entity recall compared to vanilla RAG, because we use unstructured tool to process the documents from the network, and we optimize the performance of the retrieval part when we retrieve the documents. But for the generative part, because we use the same large language model and same prompts, they almost give the same results. But of course, like our proposed intent give more accurate answer because it's use more optimization in optimizing how the content are retrieved and ranked when we structure the intent. So in summary, we have discussed the network application interaction problem, investigated how network users in very technical or non-technical users can express their intent in a human language to the network, and the network should how the intent should be processed inside the network over two stages. The first stage is try to interpret what the general intent and convert it into a well-defined intent. It uses technical terminologies that we can search the network database later on. And the experimental results has demonstrated the outperformance of our intent rags than compared to using vanilla rag and LLM directly. And our framework rely on using machine reasoning and retrieval augmented generation for generating accurate configuration or network intents. For this work, the link for the paper is available here. Thank you.